New compounds are produced all the time. And when those compounds are produced, it's up to chemists, especially analytical chemists, to be able to determine the makeup of those compounds. They have to identify what elements are included in that compound, as well as the percent by mass of each element. There are a number of experimental procedures that help us to do this, but the concept of percent composition is an important one for us. Let's say we have a 100-gram sample of a compound that has element X and element Y. Through experimentation, it's found that there are 65 grams of element X and 35 grams of element Y. The percent by mass of any element in a compound can be found by dividing the mass of that element by the mass of the entire compound and multiplying by 100. So in the case of our imaginary compound with elements X and Y, we would say that there's 65% element X there and 35% element Y. When we consider the percent by mass of each element in a compound, we call that the percent composition. We can even determine the percent composition by the chemical formula itself. To do this, we use molar masses. Let's try finding the percent composition of baking soda, sodium bicarbonate, NaHCO3. All we have to do is determine the molar mass of the entire compound, and we can use the individual masses of the elements to find the percent composition. Let's find the mass of sodium bicarbonate first. You've got the sodium, about 23 grams per mole, hydrogen, which is about 1.01 grams per mole, carbon, 12.01 grams per mole, and oxygen, 16 grams per mole. However, there are 3 oxygens in the formula, aren't there? So we have to do 3 times 16, or 48. Putting it all together, we get a little more than 84 grams per mole for sodium bicarbonate. Now we can use percent by mass on each element to find our total percent composition. Let's do sodium first. If we take the molar mass of sodium and divide it by the molar mass of the entire compound, multiplied by 100, you see we get around 27.4% sodium in that compound. How about hydrogen? We take the molar mass of hydrogen and divide it by the molar mass of the entire compound, multiplied by 100, and we get right around 1.2% hydrogen. How about carbon? We take the molar mass of carbon, divide it by the molar mass of the entire compound, multiply by 100, and we get 14.3% carbon. And lastly, for the oxygen, remember, we have 3 times the oxygen, don't we? So we use 48 instead of 16. So 48 represents 3 times the molar mass of oxygen, divided by the molar mass of the entire compound, and we get around 57.1% oxygen. So there you go. That's the percent composition of sodium bicarbonate, or baking soda. You'll notice that when all the percentages are combined, we get, of course, 100%. What if we have a compound and we don't know the formula, but we do have the percent composition? We can use the percent composition to calculate a compound's empirical formula. The empirical formula is the lowest whole number ratio of elements in that compound. By contrast, the molecular formula gives us the actual amount of each element in a formula unit or molecule of that compound. Sometimes the empirical formula can be the same as the molecular formula. For example, water, H2O. In each molecule of water, we have 2 hydrogens and 1 oxygen. That's the actual amount of each element. It also happens to be the lowest whole number ratio. But then if you consider glucose, you can plainly see that that's not the lowest whole number ratio. C6H12O6 is the molecular formula for glucose. You'll notice we can factor out a 6, can't we, from the carbon, hydrogen, and oxygen here. So if we take this down to the lowest whole number ratio, it would be CH2O. The molecular formula is always some multiple of the empirical formula. In this case, the molecular formula is 6 times the empirical formula, isn't it? We can show it this way. Molecular formula is equal to the empirical formula times some number n. Let me show you how you can take the percent composition and find the empirical formula. Take, for instance, this compound that we have. After experimentation, we find that this compound is 40.05% sulfur and 59.95% oxygen. How do we take that percent composition and calculate the empirical formula from it? The first step is very easy. All you do is convert the percentages to grams. In other words, pretend like you have 100 grams of the substance. If you had 100 grams of the substance, then you'd have 40.05 grams of sulfur and 59.95 grams of oxygen. For step 2, we want to find the number of moles for each of these elements. How do we do that? Well, if you recall the map of Molopolis, anytime we go from Gramsberg back to Molopolis, we divide by the molar mass. So that's what we'll do here. Divide by the molar mass. The molar mass of sulfur is 32.066 grams per mole. The molar mass of oxygen is 16 grams per mole. You'll notice that I have the molar masses on the bottom of these conversion factors. That will, in essence, allow me to divide, won't it? When I arrange it in this fashion, the gram units cancel, and I'm left with moles, which is exactly what I want. Now to make the calculations. 40.05 divided by 32.066 gives me 1.25 moles of sulfur. For the oxygen, 59.95 divided by 16 gives me 3.75 moles of oxygen. For the next step, I take my smallest mole amount and I divide all of the mole amounts by that smallest value. In this case, 1.25. That gives me a ratio of 1 mole of sulfur for every 3 moles of oxygen. These numbers correspond to the subscripts in my compound. So therefore I have S1O3, sulfur trioxide. That's my compound. Remember, we take the percentages and convert them to gram values. Then we find the moles of each element involved. We do this by dividing by molar mass. Once we've gotten mole amounts for each element, we take the smallest mole amount and divide all of the values by that amount. The answers we get correspond to the subscripts for our empirical formula. Here's a compound with percent composition 48.64% carbon, 8.16% hydrogen, and 43.2% oxygen. Step 1, we pretend like we have 100 grams. That means we simply convert these percentages to gram amounts. Step 2, we'll calculate the number of moles of each element. To do this, we divide by the molar mass. The molar mass of carbon is 12.01 grams per mole. The molar mass of hydrogen is 1.01 grams per mole. And the molar mass of oxygen is 16 grams per mole. Again, in arranging it this way, it allows me to cancel my gram units, leaving me with moles. When we divide 48.64 by 12.01, we get a mole amount of 4.05 moles of carbon. For hydrogen, 8.16 divided by 1.01 gives us around 8.1 moles of hydrogen. For oxygen, 43.2 grams divided by 16 gives us about 2.7 moles. Step 3, take the smallest mole amount and divide each of the mole amounts by that smallest value. When we divide by 2.7 for each one, we get values of 1.5, 3, and 1. We can't have an empirical formula that's C1.5H3O. That just won't work. So how can we adjust that to make these whole numbers? The answer is we'll multiply by a whole number. In this case, 2. Multiplying by 2 will give us whole numbers for each of our elements. Multiplying each by 2 gives us 3 moles of carbon for every 6 moles of hydrogen for every 2 moles of oxygen. C3H6O2. That is our empirical formula for this compound. So we found the empirical formula C3H6O2. But is it the same as the molecular formula for this compound? Suppose that, through experimentation, you found that the actual molecular mass of this compound was 148.18 grams per mole. How would you use that to determine if the empirical formula is the same as the molecular formula? Remember that we said that the molecular formula is always some whole number multiple of the empirical formula. So it stands to reason that the molecular mass is always some whole number multiple of the empirical mass. That means that all we have to do is calculate the mass of this empirical compound and compare it to the mass of the molecular. 3 carbons at 12.01 grams per mole each, combined with 6 hydrogens at 1.01 grams per mole each, combined with 2 oxygens at 16 grams per mole each, we get a grand total of 74.09 grams per mole. In order to know the multiple that we use, We simply take the molecular mass and divide it by the empirical mass. In this case, 148.18 divided by 74.09 gives us a value of 2. And what that means is that we'll multiply everything in the empirical formula by 2, and that will give us our molecular formula. So our actual molecular formula is C6H12O4. Okay, here's your challenge for homework. Let's say you have a compound and it is 65.45% carbon, 5.46% hydrogen, and 29.09% oxygen. Through experimentation, you find that the actual molecular mass is 110 grams per mole. What is the molecular formula of that compound? You can put your answers in the LMS. That's the end of our video today. We talked in this video about percent composition, how we can find the percent composition based on using the molar masses of each element compared to the molar mass of the compound. We discussed the difference between the empirical formula, the lowest whole number ratio of elements in a compound, and the molecular formula, the actual number of elements in a compound. Then we used our knowledge of percent composition to determine the empirical formula of a compound based on the percentages given. Hope this video has been helpful to you, but if I can assist you in any other way, as always, just let me know. Until next time, God bless.